So up to this point, we've been calculating our derivatives using the definition of the derivative. What we'd like to do here is we'd like to develop some shortcuts. So we saw several of these in the flip class video. So we'll recall a few of these here, but definitely make sure you watch that video before this one. Let's start with the easiest case. So let's say if f of x happens to just be a constant. Well, in this case, remember the derivative is asking us how does f change as x changes. So if f is a constant, it doesn't change at all. So that means the derivative is just 0 in this case. Now, for example, this can get a little confusing in the case we have our derivative is our constant is a power. So, for example, if f of x is, say, pi squared, this is still a constant. So the derivative of f here is still 0. We're going to learn a power rule in a second, and that can become a little confusing because people will think, oh, my constant's to a power, so I have to use the power rule. But you have to remember, if it's constant, the derivative is 0, even if it's raised to a power. So let's go ahead and state that power rule. So if I have f of x is just some power of x, then the derivative of f, you bring the power down and subtract 1 from the exponent. Now this works for all real numbers. All real numbers. And right now we can only show it for integers. If you think about it, if I define my function, say f of x is x to the pi, you probably haven't thought about this before, but what would like f of 2 even mean? 2 to the pi, what does that even mean? So we'll come back to this later, but what we actually need to do to define this is we need to use logarithms and exponentials. But for now, it's fine to just take it for granted that we can use this power rule no matter what the power is. So let's go ahead and see an example of why this is true. We won't show this in general. In general, you can do this using binomial theorem, but we'll just do this particular case as it kind of shows what happens in the general case. So once we've established these rules or we've stated them, we can use them going forward unless the problem tells you to use the definition of the derivative. Then you have to actually do the limit. But to establish this, let's go ahead and use the definition to see that the power rule does actually work for this particular power. Okay, so we just fill in for what f is. Now we're going to FOIL the first term out. So that will give me an x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Now notice the x cubes cancel, so I get the limit as h goes to 0, and now I'm going to get a 3x squared h plus 3xh squared plus h cubed all over h. We can factor an h out and cancel it, so then I'll just have a 3x squared plus 3xh plus h squared. And so this limit is just 3x squared, which is what we expected from the power rule. If I take the derivative of x cubed, I should bring the 3 out front and then subtract 1 from the exponent. So this shows us where the power rule comes from for one particular case. You can show it for other cases as well if you like, or we can just take this for granted that it's true. A few other rules we're going to want. So if we take c as a constant, then if I take the derivative of a constant times a function, this is just the same as the derivative, or the constant times the derivative of the function. So for example, if I take the derivative we say 7x squared. This is the same thing as 7 times the derivative of x squared, which is just 14x. We can also take derivatives over sums of functions. So if I look at the function f plus g, and I take the derivative of that, that's the derivative of f plus the derivative of g. And you should notice here I'm jumping back and forth between the prime notation and the d dx notation. It's important to be used to both of them, so I'm kind of switch back and forth just to make sure you're seeing both of them on somewhat of a regular basis. So let's see, why is this one true? Well, let's just write down the definition. So this is the limit as h goes to 0 of f plus g of x plus h minus f plus g of x all over h. And now we just write down what a sum of functions is. So this is just f of x plus h plus g of x plus h minus f of x minus g of x all over h. And now we just regroup these things and split them up. So let's put the f's together and split up the limit with the g's. And now notice this first limit is the definition of the derivative of f, and the second is the definition of the derivative of g, which is exactly what we expected to have happen. Let's try some examples. So let's let f of x be 7x to the fourth minus 3x squared plus 5x to the minus 3 halves. So we can take the derivative of this. So the first one is going to be 7, and then the derivative of x to the fourth is 4x cubed minus 3. The derivative of x squared is 2x plus 5. And now we bring down the 3 halves, and then we subtract 1 from the 3 halves. So this becomes 28x cubed minus 6x minus 15 halves, and then this will be x to the minus 5 halves. Okay, so let's try a word problem with this material. Actually, maybe let's do one more computational example first. So let's find the tangent line. At x equals 2, to the function f of x is x to the 1/2 plus x squared minus 3 all over x. Well, the first thing we can do is find a point on the tangent line. So let's plug in the 2. So this is going to give me 2 to the 1/2 plus 4 minus 3 over 2. So this is 2 to the negative 1/2. The second part is 1, so this is plus 1/2. And now for the second part, we want the derivative. Now I don't know how to take a derivative if I've got a quotient of functions. We haven't learned that yet. But what we can do is we can simplify f a little bit by just dividing the x through. So I'll have an x to the minus 1/2 plus x minus 3x to the minus 1. And now this is a sum of different powers of x. So we can use power rule to take this derivative. So we have minus 1/2 x to the minus 3 halves plus 1 plus 3x to the minus 2. And now we can plug in our point here. So I have minus 1/2, and then I have 2 to the minus 3 halves plus 1 plus 3/4. So my tangent line is not particularly pretty in this case. So I have the 2 to the minus 1/2 plus 1/2 equals, and then I have this mess here for the slope, so minus 1 over 2, 2 to the 3/2, plus 1 plus 3/4, x minus 2. Okay, now let's go ahead and try a word problem. Okay, so we have the period of a pendulum is given in terms of its length and the L and the gravitational constant G. And so this formula is T of L is 2 pi square root of L over G. So our first thing let's look at is let's find the derivative. So let's find dt dl. So the first thing we might do is rewrite our t again so it looks like something a little bit more favorable. So I can write this as 2 pi, and I can write this as L to the 1/2 over G to the 1/2. And now since that G is a constant, let's go ahead and group that with the constants, and then leave our L to the 1/2 there. L is acting as x here because it's our independent variable. So now I can use power rule with the L, so these constants out front just stay the same. Nothing happens to these. And then for the derivative, I'm going to bring that 1/2 down and subtract 1 from the exponent. Now the 2 and the 1/2 will cancel, so I'll have a pi over G to the 1/2, L to the minus 1/2. And that's our derivative. And now we might ask some questions about this. So for example, so what is the sine of dt dl, and what does it tell us about the period? Well, since g is the gravitational constant and that's positive, pi is positive, so I definitely always have dt dl is positive. So that means t is an increasing function. What does this mean? So if we increase the length of the pendulum, the period increases as well. So it's important we're able to take these new concepts like the derivative here and when we do a word problem to actually make sure we understand what it's actually telling us about. When I say a computer can calculate derivatives just fine, it's a person who needs to actually do the interpretation. So that's what we're doing here. Make sure we're good with that. So that allows us to take derivatives of sums of powers of x. Another natural simple function we might be interested in are exponential functions. So we also derivatives of exponential functions. Now we won't be able to calculate these exactly here rigorously because it's going to involve a limit that we don't know how to take yet. But we can actually just get the correct answer by looking at limits how we started off by just plugging in some values and making a good guess, and then we'll see later on that that turns out to be the correct guess. So let's take our exponential function. So let's let f of x be a to the x with a bigger than 0 a constant. Now if I want the derivative of this, I want f prime of x. This should be the limit as h goes to 0 of f of x plus h minus f of x over h. Now let's fill in what our function is. Now what we're going to use is we're going to use some properties of exponents. So if you recall, a to the x plus h is a to the x times a to the h. So I can rewrite this and now each term has an a to the x in it, so I can factor that out. And since a to the x doesn't depend upon h, I can bring that out front of the limit. So what we see then is, in order to calculate this derivative, what I need to do is I need to be able to evaluate this limit. So what we're going to do is we're going to pick a particular value of a, and we're going to do some tables, and we're going to see what this is in that case, and then we'll be able to guess the general case from that. So let's take a to be 7. So we want to guess, educated guess, but guess that the limit as h goes to 0 of 7 to the h minus 1 over h. So we got pretty good at guessing these limits in the early section, so let's go ahead and make our tables. And so let's start off and then let's take a big jump and go all the way to 1 over negative 1 over 10 to the 9. So that's a really small number. We have 9 zeros there. So if we evaluate these, we get 1, 7, 6, 8, 2, 9. These are all approximates. 1.9271, approximately 1.94402, and then this one is approximately 1.94591. Then we can do the same thing with some positive values. Now this should just be this should just be get rid of one of these zeros. So again, these are all approximate values here. Okay, so from this we could see we probably want to guess here that the limit as h goes to 0 of 7 to the h minus 1 over h is about, let's say, approximately 1.94591. And we can also graph this to see what this function's looking like. Let's put an h here. Now it's not defined at 0, so we'll fill in a spot there, and then it goes up and looks like this. And this value here happens to be, if you were to graph this and zoom way in, it's getting closer and closer to that, just like we saw from our tables above. And now it seems like this might just be some random decimal, but what we could note is that actually if I look at the natural log of 7, this is approximately 1.94591. So what we should guess then is that the limit as h goes to 0 of 7 to the h minus 1 over h is natural log of 7. So now if we go back above, if we want to abstract this, when we took a equals 7, we got this limit was natural log of 7. So this limit up here circled in red, we should guess that that is natural log of a. So we guess limit as h goes to 0 of a to the h minus 1 over h should be natural log of a. So then, if we do that, then the derivative of a to the x is natural log of a times a to the x. And that does turn out to be exactly what the answer is. So we made a good guess here from our data. In a special case of this, is notice if I take the derivative of e to the x, well, natural log of e is just 1, so this just gives me e to the x back. Okay, let's try an example using our new derivatives. So let's let f of x, let's say this is x raised to the pi squared plus pi squared raised to the x plus pi squared. And let's find f prime of x. So there's a lot going on here, so we have to be careful. So for the first term, notice this is just x raised to some power. So for this first term, we can just use power rule. The pi squared comes out front, and then I subtract 1 from the exponent. Now when I look at the second term, this is an exponential function. My a here is pi squared, so this becomes natural log of pi squared raised to the x. And then the last term here, pi squared, this is the one where I said it, people can often get confused and think to use power rule here and think the derivative is 2 pi. But actually, pi squared is a constant, so this is just plus 0. Okay, so let's try some more examples. Okay, so in 2009, the population of Mexico was about 111 million, and it was growing at about 1.13% annually. In 2009, the population of the United States so this was 307 million and growing at 0.975% annually. Okay, so if we measure growth rate in people per year, which population was growing faster? In 2009. So to do this one, the first thing we need to do is we need to come up with equations for each of these. So let's say the population in Mexico. Let's come up with the equation for that first. So we'll write this as m of t. So we can say there's 111 million is our initial population, and now it's growing at 1.13%. So if you don't remember how to do these equations, you can go back and watch the video on exponential functions for a refresher. And then the population in the United States, let's call this S of t. This is 307, and this is at 1.00975 t. So we're looking for the rate of growth here, so we want people per year, so we want to look at the derivatives of these. So this will be 111, then I'm going to have natural log and for population for the United States, it's going to be 307. So those are the derivatives overall. And now we're asking which population was growing faster in 2009. So 2009 is going to correspond to when t is equal to 0 based upon how we set this up. So we want to compare m prime of 0 and s prime of 0. So m prime of 0 is going to be 111, natural log of 1.0113. And if we were to put that into a calculator, this is about 1.247, and this is million people per year is what this is what the population of Mexico is growing at in 2009. And if we do the same thing for the United States, we get 1.00975, and this is approximately 2.979 million people per year. So when our question was which population was growing faster, the United States population was growing faster. Okay, so the last two functions we want to look at here, so our last two functions for this section are cosine x and sine x. So we're going to go ahead and look at sine x, and then we'll just stay with the result of the cosine x is afterwards. So let's look at that. So let's let f of x be sine x. So then the derivative is going to be the limit as h goes to 0 of sine of x plus h minus sine x over h. Now this doesn't look like something that's so easy to work with, but what we can do is we can use the trig identities to simplify this a bit. Now I wouldn't expect you to remember these, but we can go ahead and look them up. So we've split up this sine of x plus h using the trig identity. So this becomes sine x cosine h plus cosine x sine h, and then I saw that minus sine x there. This whole thing over h. And now we can go ahead and split this up and write this as the limit as h goes to 0. Let's go ahead and bring all of the ones with the sine x together and factor that sine x out. And now the terms that have just x's can come out front of the limits. And so now what we need to do is we need to figure out what these limits are. So we're basically going to do the same thing we did before, and we're just going to use some tables to fill these in. So the first one's pretty easy, the sine h over h. This converges super quickly. So if I put just this value in, this is already going to spit out just 1 when I put it into the computer. And just pick another value much smaller, and this still spits out 1. And same thing if you come from the right-hand side. Spits out approximately 1. So that leads us to guess that the limit as h goes to 0 of sine h over h is equal to 1. And then the other limit we need is with the cosine. This one doesn't converge quite as quickly, so we'll see some change in this. So if I do minus 0.001, this is about 0.0005. And then if I do a large one, this is approximately 0. And same thing for this side. So we're going to say that the limit as h goes to 0, cosine of h minus 1 over h is 0. So now if we go back up, we can see what's happening with going on here. So this term here, this one is going towards 0, and this one is going towards 1. So that means all we're going to be left with is the cosine of x. So the derivative of sine x is just cosine of x. And now if we were to graph these functions, it might not be so surprising if I were to just give you the graph of sine x, and I told you once I give you this graph, I want you to graph the derivative of this function. Well, what would the derivative of this function look like? Well, it looks like here is at its biggest spot, so we'll put that up here. Over here, it's flat, so the derivative should be 0 there. Most negative, back to 0, back up, and similarly this way. And so you can see, what does this look like? Well, this looks exactly like cosine x. And now, if we were to do this with cosine x, not going through the whole same calculation, so what about if I were to look at cosine x? Well, let's graph cosine x and see if we can get an idea of what the derivative might be for this. So this is my y equals cosine x. And now we can see the derivative here is 0. But now, what's going on? Well, the tangent lines are negative here, so we're going down. And then we're coming back up. And then, and similarly going this direction, going up, and then back down, and so on. So this looks almost like a sine graph, except for it's switched around. So this is actually negative sine x. So in this regard, we get that the derivative of cosine of x is negative sine x. Now, most of you are just going to memorize these, and that's perfectly fine, but I would say it's good to understand what we just did with these pictures here, because it can be the case you get on an exam and everything you memorize gets a little hazy because you get nerves. And you'll remember, well, one of the derivatives is the other one, and one of the derivatives is the negative of the other. And so just by graphing these, making these graphs real quick, you can see which one is just the derivative and which one is the negative of it. So that can be useful for helping your memory. Okay, let's try one more example to round out this lecture. So let's let f of x be equal to 2e to the x plus 5 x to the 7/3 plus 3 sine x. We want to take the derivative of this function. So the derivative of 2e to the x is just 2 times the derivative of e to the x, which we saw is just e to the x. For this next one, we use power rule. So we bring that 7/3 down, and then we subtract 1, so that will give me 4/3. And then the derivative of 3 sine x is 3 times the derivative of sine x, which is just cosine x. And so if we want to simplify this a little bit, we can. So this is 35 thirds x to the 4/3 plus 3 cosine x. So that gives us some derivatives of some of our basic functions. In the next section, we're going to use these, and we're going to see how to build up to take more derivatives by looking at how to take derivatives of powers, or not powers, but products and quotients. So that will be our next section.